All right, so part C. Part C, we got example 7c. We got the limit as x goes to infinity of x to the 1 over x power. Gorell's already guessing 1 if it was a multiple choice question. Okay, and we'll see if he guessed correctly. He might be getting it wrong, but he's making good time, right? It's like back in the day, and today everyone types with like thumbs, on their phone, and some of y'all on a keyboard are hunting peckers, right? Yeah, you hunt for, and then you peck with your fingers. You're not hunting peckers. That'd be like going after roosters with guns. You're hunt and peckers. But when you used to hire a secretary, it was one of the big things was like how many words per minute can you type, right? And it was like, wow, you could type 50 words a minute or 60 words per minute. So Gorell would be kind of the guy that just answers one and goes on to the next. He'd be kind of the guy that say, I could type like 100 words a minute, but yeah, all my words are misspelled. Okay, they're all misspelled, but I can hit the keys very fast. All right. All right, let's go ahead and do that. Never not first. You plug in and you get infinity to the 1 over infinity power, which is 0. Yeah. Is it 1? Anything to the 0 power is 1. But what about something that's getting infinitely large to the 0 power, like infinity? What is infinity times anything? Infinity. Should be infinity. So, again, on the one hand, you have a multiplicative situation going on, infinity times infinity times infinity. It's approaching infinity. And then something to the 0 power, which is kind of making it small. So there's a tug of war. So this is indeterminate form, and it's the exponential variety. So we got the couple steps, right? We got to make it into the multiplicative case, and then into the quotient case, and then we can try lopping it, right? So what do we do first, class? Not yet. No, you got to set it equal to y. You can't take the natural log of expression, because if you take the natural log of expression, it changes the expression, right? Like 1 versus the natural log of 1, right? Or holy cow versus the natural log of holy cow. Changes the expression. Now we can take the natural log of both sides. And of course, the limit can just kind of stay in the front, and we get the natural log of x to the 1 over x power. And of course, I'm not going to write 2 lines. I'll just animate it. Boom, into the front you go. And now let's try direct substitution. It's still multiplied. 1 over x approaches 0, and the natural log of x as x goes to infinity approaches infinity. So now it's in the multiplicative case. I need to turn it into the quotient case. So which factor do you want to bring to the bottom? Yeah, let's call the 1 over x in the numerator. Let's just call it an x in the denominator, right? That is a super obvious one. Or it should be. And now when you plug in, you get infinity over infinity. The line goes to infinity, and the ln goes to infinity. And so now we're in the multiplicative case. And so, again, we're not using log diff, so we don't take the derivative of both sides. We're just evaluating the right by L'Hopital's rule. So we get 1 over x all over 1. And now, anything divided by 1 is itself. So if you use direct substitution, what is 1 over infinity? It's 0. 0 divided by 1? 0. So answer choice A on a test might be 0. Or it might be B or C or D. There's only 4 answer choices. So if we solve for y again by e'ing both sides, we get y equals e to the 0, which was? 1. Wow. So Gorell got it right by guessing 1 to begin with, which would be kind of like if you put monkeys at typewriters. They say if you sit them there long enough, they'll eventually type out the works of Shakespeare. Okay? And so, yeah, it's kind of an anomaly, but yeah, you'll eventually be right if you answer 1 every single time you see these. Okay. All right. Macbeth, as written by Cletus the monkey. I know, Cletus sounds like a good name for a chimp. All right. Bonzo, right? Y'all know Bonzo. Bedtime for Bonzo, or is it Bongo? Ronald Reagan's movie, Bedtime for... Someone Google it. Anyone have Google? Anyone know how to search for anything on the World Wide Web? Ronald Reagan, Bedtime for Bonzo or Bongo? Man, I should know. Is it with a Z? Bedtime for Bonzo. Yeah, I think that's what I said first. Bedtime for Bonzo. That's good. Our future president. Was bedtime for Bonzo? Yeah, we'll just say Z. Okay, cool. All right, so any questions then on how to handle exponential indeterminate forms? 1 to the infinity, 0 to the 0, or infinity to the 0? All right, Bonzo did not want to go to bed. Here's a fun one. That doesn't mean the previous ones haven't been fun. Just like, redundantly, here's another fun one. The limit as x goes to 1 of the integral, from 1 to x of cosine of t dt over x squared minus 1. Never not first. When you're evaluating a limit, it says x goes to 1. So what do you do first? Never not first. Direct step, right? So in the numerator, what would be the integral from 1 to 1? 0. Cool. And the denominator, you plug in 1 minus 1 is 0. Yes. It's the quotient form. It's indeterminate. I can use L'Hopital's rule. So we'll lop it. The limit as x goes to 1. How do we take the derivative of the numerator? Yeah, it's the second part of the fundamental theorem of calculus, right? So remember the general rule, and we'll just review the general rule first. The derivative of the integral is you plug in the top for t times the derivative of what you plugged in. So that'd be cosine of x times 1. And then minus you plug in the bottom times the derivative of what you plugged in. That would be minus cosine of 1 times 0. And so that always works. So this would be the special case when you're going from a plain old number to a plain old x. The derivative is just the integrand, but now it's a function of x instead of, in this case, t. And of course, the derivative of the bottom is 2x. Now we try direct substitution, and we get cosine of 1 all over 2. What is cosine of 1? Is it 0? That's cosine of 1 degree or 1 radian? 1 radian, which is about 57 degrees, which is about pi thirds. What's cosine of pi thirds? It's about 1/2. So cosine of 1 is going to be a little bit bigger or smaller than 1/2? Okay, so if you're at 60 degrees, it's 1/2. If you have to rotate down, your triangle is getting wider. Should be a little bit bigger than 1/2. So cosine of 1 is something slightly bigger than 1/2. And then 1/2 of 1/2 is 1/4. So that answer should be something a little bit bigger than 1/4. So maybe not 0.25, but maybe 0.251 or 0.26. But you don't need to know that. If this were a non-calculator question, this would be the answer choice. Yeah. So you got to be careful there. Cosine of 1, it's not 1 pi, right? Cosine of pi would be -1. That's just cosine of 1 radian, about 57 degrees. So there it is. Was that fun? Yeah, good. It was fun easy. There you go. It was fun, but it was also fun easy. Okay, good. Just a good way to kind of throw in a second fundamental theorem of calculus, or fundamental theorem part 2 at you. All right, that's example 8, where we just completed page 4 of 5. Any comments or questions so far? It is National Doodle Day, right? Did I already say that? I didn't. Did you read that? You got to be careful if you tell someone, hey, happy National Doodle Day. They'll be like, is it Doo-Doo Day? And you're like, no, it's not Doo-Doo Day. It's Doodle Day. Okay? Be careful how you celebrate. Uh-oh. Example 9 should be bolded. It's not. Does that mean it's not as important? I don't know. I just forgot to bold it. Here's one even more fun. Here is one even more fun. Looks like we're missing a word in there or something. Okay. So I kind of really messed up here. Didn't bold it, missed a word. This is similar to the 2016 free response question on the BC exam, question 4. Do you remember that one? No. Okay, good. You probably did not take that test. And you probably did not spend your free time just scouring through old free response questions yet. But 2016, that's pretty fresh, right? That's pretty fresh. This was the 4th question on the exam. So your first 2 questions are with the calculator. You have 2 free response questions with the calculator in 30 minutes. And then you put the calculator away and you work 4 questions without a calculator in an hour. And if you need to go back to the first two free response questions, you're allowed to do so, but you won't be able to use your calculator anymore. But you could still give exact answers and put units and set up integrals or something like that. So that's how it works. So this would be a question that does not involve a calculator. Let's go ahead and go through it. Consider the differential equation dy dx equals y squared minus 1/2 x. How do you consider an equation? Can you get credit for that? You ponder it. You're kind of doing it. Yeah, if you kind of rub your chin a little bit, kind of evidence that you're considering it. Yeah, I guess. Yeah, I don't know. Just make sure that the test proctor sees you doing that. So just get Mr. Garnsey's attention. Garnsey, hey. And be like, oh, do I have something on my chin? What are you trying to communicate? I looked in the mirror this morning. I didn't see anything, but sometimes I get hungry and it just ends up with egg on my face. So, all right. Find the second derivative in terms of x and y. So this is what's important. It doesn't say just find the second derivative. It says find it in terms of x and y, which means in the end, you're going to have numbers, operational symbols, and x's and y's, not dy's and dx's. Okay, so how are we going to get to the second derivative from the first derivative? Take the derivative of it. Now, because it's already explicitly solved for dy dx, the fewest number of moves you can make is just go straight to d squared y over dx squared. Okay? If you want to put in the front d dx colon, that's not bad. Remember, that kind of is the verb that says, here's what I'm about to do. I'm going to take the derivative. Okay, so the derivative of y squared with respect to x, implicitly, right, is going to be 2y to the first times dy dx. Chain rule. Good. Minus 1/2 x becomes minus 1/2 times the chain rule dx dx, which of course we don't need. So if you stopped right here, would you get full credit? No, that's in terms of dy dx. You would probably get a check for that, but now we just need to substitute in. So dy dx, parentheses, that's going to be y squared minus 1/2 x minus 1/2. Now if you stopped right there, that's good. That's in terms of, bless you, that's in terms of x and y. Would you distribute the, bless you? Would you distribute the 2y on your own? Or would you stop here? I would stop there too, yeah. Until you need to simplify it, don't do so. Now sometimes they might say, show that dy dx equals, and they'll give you a final form to shoot for, and then you would need to try and distribute and match their form. But that usually happens when they give you a function and you need the first derivative. They'll say, here's the first derivative, confirm that it is. So I'll leave it like that for now. All right, part B. Let y equals f of x be a particular solution to the given differential equation whose graph passes through the point 2, -1. Does the graph of f have a relative max, a min, or neither at the point? Justify. So we're at the point now where we can have these free response questions that cover anything in the whole wide world that we've covered so far this year. So first of all, there's a couple things we have to do. First of all, local or relative max or mins, extrema, can only occur at what type of x values? At what type of x values? Critical values, yeah. Critical values are places where the first derivative is either what or what? 0 or dne, yeah. So let's go ahead and take the first derivative, which they gave to us, right? dy dx equals y squared minus 1/2 x. And I'll cut that, paste it down here. And let's see, is it ever undefined? That's the one that most students kind of just overlook. Is the first derivative ever undefined? No, I don't have any variables in the denominator, and I don't have any variables under a square root where negatives would be prohibited. So it looks like for any value of x and y, I'm going to be able to plug it in there and get an answer. Okay, so I'll just set it equal to 0. Now, you will get a check for simply setting it equal to 0, so don't not set it equal to 0. And you can get that by either setting the expression y squared minus 1/2 x equal to 0, or by saying dy dx equals 0, either way. But of course, we want to set the expression equal to 0 because then we have something to shoot for. How am I going to solve an equation that is, equal to 0, but it's got two variables in it. Do what? Okay, so y squared equals a half x. Yeah. Then what? Yeah, in this case, I'm not trying to solve for x. It's asking, is there a local max or min at this point? So, right. So I'm not going to necessarily solve for x or y. I'm going to take this right here and just verify and see if when x is 2 and y is -1, do I get a 0? Okay? So let's see. We'll say dy dx evaluated at 2, -1. That's the way you show it with Leibniz notation. Okay? So if you did this right here in your attempt to solve, you haven't said anything wrong. But what I'm going to do down below is just evaluate it and see if it is 0. So we'll plug in a 2 for x and a -1 for y. So -1 squared is 1. If you plug in a 2 for x, you get -1. That's 0. So we do get 0, right? So now we'll say, so 2, -1 is a critical value of, and do they name the function f? Yeah, they said y equals f of x. So it's a critical value of f of x. So that's the first thing. Now that we know it's a critical value, now it's a possible, potential, prospective, plausible local max or min. If you would have plugged that in and gotten like a 5 there or a -1, it would be game over, right? You would just say, no, it's not a critical value, therefore there's no local extrema there. All right, so now there's two ways to determine if the critical value is the location of a max or min. We could do the first derivative test, where we plug in values to the left and right and look for a sign change, or we use the second derivative test, which looks at the concavity at that point. Which one here is more suitable? Yeah, they're trying to kind of lead you to the second derivative test because they had you find the second derivative on part A. By the way, if you wanted to do the first derivative test, would it even work? You have to pick a point on the graph that's to the left and to the right of x equals 2. Do we know any other point on the graph of f other than 2, -1? We don't. Okay? You can't just arbitrarily choose an x and y value and say, it's on the graph to the left and on the graph to the right. So we can't even do that. So that's the real power of the second derivative test. It doesn't require information on either side. So now we'll have to say the second derivative of y with respect to x, evaluated at the same point, 2, -1. And we'll plug that into the second derivative that we got above here. And again, we don't need to distribute. We can just kind of plug it in. So I get 2 times -1, which is -2, times y squared, which is -1 squared, which is 1, minus 2 times a half is 1, and then minus a half. Now, I don't really have to simplify that, but I kind of want to because I need to see if it's positive or negative. So I'll just take a risk. 1 minus 1 is 0. 0 times -2 is 0. 0 minus half is -1/2. All right, so we got a -1/2. What's more important, the fact that it's 1/2 or the fact that it's negative? The fact that it's negative. So now we have to say less than 0. That's a justification. Now, here's what I recommend you do. We know that if the second derivative at that point is less than 0, the graph of the solution curve f is concave down, right? So remember, negative second derivative means concave down like a frown. And then if you just kind of button the lip, you can see then that it has to be a local max, okay? So now all you have to say is, so f has a, and you could say local max, but they actually use the term relative. So try and reuse their words. Has a relative max, and that's appropriate to abbreviate max, at the point 2, -1. Do you need to say by the second derivative test? No, you don't. You can. No, you wouldn't be rubbing it in their face. You would just be further demonstrating or communicating your knowledge. But we're using the test, okay? We don't have to say that we're using the test, right? So what are they going to be looking for? They're going to be looking for, did you show it's a critical value? Did you show the derivative 0? then did you come up with the sign of the second derivative, and then did you make your correct claim based upon the sign of the second derivative? Okay, I mean, you could go on and say a lot. So if the second derivative is less than 0, the graph of f is concave down at the critical value, and therefore by the second derivative test, the solution curve f of x has a relative maximum at the coordinate 2, -1, and I like cheese. Right? I don't know. Yeah, you can say a whole lot, right? And that wouldn't be wrong, right? Because that's an opinion. But if you say we get cheese from trees, now they'd be like, oh, now I got to research that. Is there a tree that actually has cheese on it? And they look it up, and if they couldn't find one, they'd be like, now you misspoke. You said more than you needed to, and it's wrong. So now you lose a point. Okay. Part C. Let y equals g of x, another function, be a particular solution to the given differential equation with a different initial value, -2, 3. Find that. Oh boy. Show the work that leads to your answer. Oh, by the way, do you think that we're going to ask you on this question at some point to solve the differential equation and define the actual particular solution or the general solution? They sometimes do, but is this going to be a separable differential equation or non-separable? This one's non-separable, right? Because you have a x and a y in two separate terms, and the only way to separate variables is if you can factor by multiplying or dividing your x's and y's. And so we're not going to be able to separate these variables. So they're not going to ask you to find the particular solution. They might ask you to sketch a slope field. They might ask you to do Euler's method, or the questions that we're actually being asked right now. All right, so evaluating a limit. That's not too bad. The limit as x goes to -2. Never, ever, ever, never, ever, not first. We do what? Plug in. So let's go ahead and plug in. That would be g of, in a highlighter, nope, I don't think so, g of -2 minus 3 all over 2 times -2 plus 3 cubed minus 2. Is that an exact answer? Can we stop right there? Bless you. No, we can't, because we got a g of -2 there. What's g of -2? 3. Okay, 3. So we get 3 minus 3 all over 2 times -2 plus 3 cubed minus 2. Can we stop right there? That's the numeric answer, right? Right. So you got to be careful, right? You got to be careful. If you stop at tangent of pi thirds, that's an exact answer. If you stop at tangent of pi halves, that's undefined. No good. So this one ends up being 0 over 0, which is an indeterminate form. You do want to show 0 over 0 because that is kind of that's the way that you're showing that you're going to use L'Hopital's rule. Now you don't have to say by L'Hopital's rule, but if you want, you could do this. You could say, let's lop it, right? That would be kind of cool, right? If an AP reader saw that, they'd be like, hey, I kind of like that, like a gardener, right? Would do with crepe myrtle this time of year. It is safe to trim your crepe myrtles back now because the last freezes were, I think, supposed to be a big winter bomb blast hitting the northeast again this weekend, but maybe it won't get to us. All right, so let's lop it. So notation. Make sure you write your limit here. And remember, we're not using the Hody-High rule. We're just using the derivative top and bottom. So that's going to be g prime of x minus what? 0. And at the bottom, we got senior chain rule, which is going to be 6 times x plus 3 squared times 1, derivative x plus 3, and then minus the derivative 2, which is 0. So I'll just close the parentheses there and have some awkward space. It's all right. Now guess what we try next now at this moment? Let's try plugging in again. So now we get g prime of -2 all over 6 times -2 plus 3 squared. If you look at the bottom, what are we getting in the bottom? 3 minus 2 is 1, 1 squared is 1, 1 times 6 is 6. Is this going to be a conclusive answer if we get a 6 in the bottom? Yeah, because 6 is not 0 or infinity. So can we stop there? Is that numeric? No, it's not. We need to find g prime of 2. How are we going to find g prime of 2? Plug it into the derivative, right? They gave us the derivative. It says that dy dx is equal to y squared minus 1/2 x. So with tunnel vision, I'm going to come up there, cut it, and paste it right here. And notice our derivative requires both the x and the y value to evaluate it. So if I'm trying to find g prime at -2, I need to know the x and y value at -2 on the solution curve g. Oh, they did. Yeah, there it is, -2, 3. So we get dy dx evaluated at, what, -2, 3? Yeah, -2, gamma 3. And we plug in very carefully, right? 3 squared is 9. And if we plug in a -2, negative times negative is positive. 2 divided by 2 is 1. So we get +1, which is, I'm going to go for it. You don't have to simplify, but I'm going to go for it. 11 minus 1. Oh, that's rubbing it in their face, Colin. Yeah, that's 10. Okay. It's 10. All right, so I'm done with 10? No. Oh, no. I got to come back over here and say 10 over 6 times -2 plus 3 squared. Now can I stop there? You can stop there. That's okay. No, that's not rubbing in their face. Yeah, I guess. Yeah, let's see what this is. I'm just curious. We get 10/6. 10/6 is the same as 5/3. Do you get bonus points for going with 5/3? Absolutely not. No. What if you put like 5/2? Yeah, now you're wrong, whereas if you would have stopped on the line above, you were correct. So sometimes when you get a check, you bank it and you can't lose it again. But in this case, yeah, you could certainly lose it.
So justify, say like 5/2, say
if 2 equals 3.
It's like rubbing it in their face. It's like whatever you get the
All right. Don't use a number as a variable. Okay. Unless it's a Roman numeral. Okay. Does G equal something? Well, any final answer should have numbers in it. So like sometimes they ask you for an integral setup but do not evaluate. If it's an ugly x value that you said x equals and you stored it as a, do not leave a in your final answer. For an intermediate setup, that's fine to use like a and f of x in your integrand. But if they say set up but do not evaluate, you want to put your 3 decimal value for a and then put whatever f of x is in there. So for your final answer, don't have symbols that are representing things. Yeah. Final answer? No, final answer. Like Regis on Who Wants to Be a Millionaire, right? Is that your final answer? Is that your final answer? Yes, right? It was a moth. Okay. Letter D. Let y equals h of x be a particular solution to the differential. We got all kinds of particular solutions. F, G, and now h. This one passes through the point 0, 1. Use Euler's method starting at 0 with two-step of equal size. Two-step is these, there should be an S there, with 2 steps of equal size to approximate h of 1. So that was the BC question. The AB had the same thing, but they said use the linearization of h at 0 to approximate h of 1. So remember, linearization is tangent line approximation, and all that is it's Euler's method with 1 step, right? So we're doing Euler's method with 2 steps. So ours should be a little bit more accurate. All right, so let's go ahead and make our Euler's method columns. So we got x, we got y, we got dy dx, that's the slope. All right, and we'll call that m. And then once you find that, you need to find delta y. Delta y is m times delta x, and that comes straight from the slope formula. And then we get our new y value, which, of course, you don't have to write it, but it's y, the old y value, plus delta y. So those are your columns, and this just systematically is a method for getting the right answer. All right, we're starting with the point 0, 1, 0, 1. All right, we need to figure out delta x. That's important. Delta x is b minus a over n. So it's going to be where you want to end up minus where you're starting over n. We want to end up at 1. We're starting at 0, and we have 2 steps, so it's a half. Just be very, very careful if you're ever using Euler's method in reverse. We've seen that, right? We've done that. Then you're going to have a negative delta x. But in this case, delta x is positive. All right, so let's go ahead and plug it in. I'm going to go ahead and, again, it's kind of nice to have the derivative nearby. And, of course, we get tunnel vision sometimes with iPads. All right, so there we go. So now if you plug a 0, 1 in, you're going to get a 1 minus 0, which is 1. Delta y, we get 1/2. And we get 1 plus a half is 3/2, or 1.5. Okay? So whether you want to use decimals or rational numbers, kind of up to you. And so now we add delta x. So we got a 1/2. Let's finish the problem first. I'll keep it as 3/2 for now. We don't have a calculator. It's probably easier to square fractions than decimals. All right, so if we plug that in now down here, and you could use the paper at the bottom for your scratch work. 3/2 squared is 9/4, minus a half of a half is a fourth. That gives you 8/4, which is what? 2. So we'll put 2 there. All right, and so delta y is 2 times a half, which is 1. And now we add that, so 3/2 plus 1 is the same as 3/2 plus 2/2, which is 5/2 or 2.5. And then if you add another half, you end up with 1. And if you bring that y value around, you get 5/2. Now here's where you don't want to make the mistake. You don't want to go on another iteration, right? You're staring at your ordered pair right there. So do you stop and just box it right here? No. Now you come down here, so, and then you answer the question. H of 1, what comes next? Squiggles. Squiggles, 5/2, or 2.5. Okay, so that would be the BC. Let's quickly do the AB. We have time. Let's do the AB. Use linearization of h of x at 0 to approximate 1. Now, if you want, you could do Euler's method. Just do it with one step, but your delta x is going to be not 1/2, but 1. Okay? But let's just do it the way that we did it back in the day. Let's go ahead and write the equation of the tangent line. So let's go ahead and find dy dx at the point 0, 1. That gives us our slope. So if you plug it in, you get a 1 minus 0, which is 1. So L of x, the equation of the tangent line, is in Taylor form, the y value of 1 plus the slope of 1 times x minus the x value of 0. All right? So there's linearization. I'm going to finish the problem. Phone call can wait. All right. So now we'll say h of 1 squiggles L of 1, which equals 1 plus 1 times 1 minus 0 is 1. And so we end up with 2. And we've already got the squiggles in there. So there you go. This could be an AB or a BC problem. But anytime that you're going to be asked to do linearization, it's going to probably be an Euler's method. And again, notice they only ask you to do 2 steps, right? They're not going to make you do like 10 steps or 5 steps. If you could do 2 steps, you could do whatever. So they don't need to test your endurance, right? They just need to test to see if you know how to do it. All right, so that finishes this section. If you want, we can look up, oh, then never mind. Well, we can look up the scoring guidelines. How much time do we got? Yeah, we got 13 minutes, right? Yeah. They did come on a little early. Let's go ahead and look up the scoring guidelines for this one, 2016 BC4. 2016 BC4. 2016 BC4. 2016 BC4. 2016 BC4. 2016 BC4. BC4. There's 1, there's 2, there's 3, here's 4. Hey, okay. So let's look at the scoring guidelines. Part A, the resolution's kind of bad, but I'll walk you through it. Part A, You got 2 points for the second derivative in terms of x and y. So you'll probably get 1 check for the first derivative where you had the dy dx in it. That's usually where the first check comes from. And then if you correctly replace dy dx in there with parentheses, then you get the second check. So that's 2 points out of 9. Part B was only worth, only worth 2 checks. And I don't want to say only. It's worth 2 checks. Conclusion, justification. So again, they're verifying it's a critical value. They're finding the second derivative. They're saying it's less than 0. They use the word thus. It's kind of pompous and pretentious. We use the word so, right, which is goofy, but not pretentious. Therefore, the graph of f has a relative maximum at the point -2, 8. So notice they also did not talk about the concavity. They did also not say that we're using the second derivative test. So the 2 points, conclusion, did you say it has a relative maximum there? And then you got 1 point for both, verifying it was a critical value, as well as the sign of the second derivative there. Okay, so now we got 4 checks out of 9. Part C, it was worth 3 checks. Now, if you notice, here it is. You got 2 checks for, they don't have the nurse's hat. I don't know if you can see it from where you're at. HOSPITAL rule. 2 checks for the hospital's rule. When you drop the nurse's hat, which is a what? A feng shui? What did you say? Circumflex. It does not, that doesn't make the S sound, does it? So I have issue with that. L'Hôpital's rule. You got 2 checks for L'Hôpital's rule. How hard was L'Hôpital's rule? It was not hard at all, okay? 2 checks for that, and then 1 check for the answer. And then in the end, you got 3 checks for the last part. You got 1 check for actually doing Euler's method, okay? And notice they don't use the tabular format on their scoring guidelines. You get 1 check, essentially, you will, for having your tabular or your chart, the method itself, and then 1 then for saying that it is approximately whatever. Okay? So there you go. That's a 9-pointer. Was it that bad? Wasn't that bad at all. Wasn't that bad at all. Okay. I don't know if we can pull up the scoring statistics to see what the average was, but if we do, I'll do that off the video. So anyway, there you go. And let me zoom in then so you can actually see it. There it is. Using La Hospital's rule. If he were alive today, if he were alive today, he would probably, I don't know, what would he do? He would probably try to steal credit for spelling it like that, right? I don't know. Giulimi L'Hôpital. All right, so we are done with 6.5. When would y'all like to turn the worksheet in? Monday or Tuesday? Tuesday it is. Okay. Worksheets due Tuesday. We're going to move on, though, on Monday, so don't let the worksheets pile up. You should be doing a little bit every single day. And that's how you have